Now, let's put all these three pillars together with the detailed real world example, that of transforming a rate limiter. This case study will show you exactly how to apply design reflective principles to turn a brittle, monolithic piece of code into a flexible, extensible system. Now, here's a scenario. We need to limit users to 100 requests per minute for our API. But we know from experience that requirements will evolve. We'll need different rules for different user tiers, different algorithms for different use cases, and the ability to adjust policies without code deployments. Now, this is a perfect example of a problem where most developers initially focus on making the code work, but then struggle later when requirements change. Now, here's a typical non reflective implementation that most developers would write initially. At first glance, this looks reasonable. It works, it's relatively short, and it solves the immediate problem. But let me show you why this approach will cause pain later. First, we have primitive obsession everywhere. The user ID is just a string, but conceptually, it represents something more specific, a user identifier with a business meaning. The max request and time window millis are just integers and longs, but they represent business rules, which are rate limiting policies. Second, we have leaky abstractions. This class exposes its internal algorithm. It uses a sliding window counter implemented with a map of queues. Anyone who uses this class has to understand these implementation details. What if we later decide that a token bucket algorithm would be better for certain use cases? We would have to gut this entire is allowed method. Third, the logic is brittle and monolithic. The class is doing too many things. It's managing storage, it's implementing the sliding window algorithm, it's handling time calculations and making policy decisions. What if we need different rules for premium users? What if we need to persist rate limiting data across server restarts? What if we need to redistribute rate limiting across multiple servers? Each of these reasonable business requirements would require major surgery on the central class. It's closed for extension and vulnerable to change amplification. Now, let me walk you through the transformation step by step, applying each of our three pillars. The first step is to eliminate primitive obsession by giving our concept proper names. We create small focus types that represent business concepts. This is where we are applying the third pillar. Now, look at how much clarity this adds immediately. A rule isn't just two random numbers, it's a cohesive business concept that represents a rate limiting policy. A request identifier isn't just a string, it's a typed identifier with validation logic. These types also serve as a natural place to put business logic. The rule record validates its input, ensures we can't accidentally create invalid rate limiting policies. Next, we identify the core secret that might change, the rate limiting algorithm. Different algorithms have different characteristics. Sliding windows are accurate but memory intensive. Token buckets handle bursts well. Fixed window are simple but can allow bursts at boundaries. We hide this algorithmic complexity behind a stable interface. This interface represents the stable concept of checking if a request should be allowed, while hiding all the algorithmic complexity behind it. Now, we can create specific implementations. Here's our original sliding window algorithm, but now it implements a new interface and uses are domain objects. Notice how the algorithm is now cleanly separated from the configuration. The sliding window strategy doesn't know what the specific limits are. It just knows how to apply whatever rule it is being given. Finally, we create a service that composes these building blocks. This service doesn't know how any specific strategy works. It just knows that it can use one. We also go ahead and use a builder pattern to make configuration clean and readable. Now, let's see how this design reflective version is used. The setup code reads like high level configuration manifest. But here's where the magic really shows. What if we need that bucket algorithm for premium users who should be able to handle traffic bursts? With the original monolithic design, we'd have to rewrite the core is allowed method. With our design reflective approach, we can simply create a new strategy and we can plug it into the service without changing a single line of existing code. We've achieved a system that is robust, clear, and generally open to the future. New algorithms can be developed independently, tested independently, and deployed without risk to existing functionality. Let me bring everything together by highlighting the fundamental mindset shift that makes design reflective code possible. Traditional programming education teaches us to think how to make computers do things. We learn algorithms, data structures, and language syntax. We focus on making our code work correctly and efficiently. This is important, but it's not sufficient for building maintainable systems. Design reflective programming requires a different mindset. Instead of asking, how can I make the computer do this? We ask, how can I model this business process clearly in code? Instead of focusing on implementation details first, we focus on the domain concepts first. Now, this transformation isn't just about code quality, it has real business impact. New developers can understand domain reflective code much more quickly because it speaks the language of the business. Changes are safer and more localized, reducing the risk of introducing bugs and the cost of regression testing. When business requirements change, the code change is predictable, localized ways rather than requiring system wide modifications. And domain reflective code serves as executable documentation that stays in sync with the actual system behavior. We also get well structured code that resists entropy and remains maintainable over time.